welcome back to ViViMaT. Our first Q&A session continues with Cangyu, Antje Dollmann, and Francesc Pérez-Ràfols right after this message. Codings is a peer-reviewed journal of codings and surface engineering published online by MDPI on a monthly basis. Okay, how about Carsten does one, huh? Let's let him ask somebody.
What about Cangyu? Because I think Beijing is also pretty late now, so maybe it's a good idea to ask him a few questions. So first of all, maybe a funny comment from Stefan's side. He was saying like, so do you anything except publish in physical review letters? I think your track record is quite impressive when we saw your publications. So what about that?
Thank you, Carsten. Thank you, Stefan. Well, is that a serious question? So
it was just a funny side comment.
Okay, so
not a serious one.
I like basketball actually. Well, I can say that I play a lot of basketball other than publications. Well, seriously, so I'm currently so I've got my PhD degree 2 years ago. So I'm currently working in a research institute called the Institute for Superlubricity Technology. So basically, what we're doing right now is take advantage of the superlubricity, the phenomenon, which is quite fascinating. The friction and wear is almost zero between the directly contacted surfaces. So this system is very interesting because we can do both fundamental science, which leads to some publications, of course, and also some applications. Well, for the applications, we're right on the starting of period of the research because we're trying to build our first prototype. Yeah. So what we want to do is build something like micro devices with ultra low friction, which is previously maybe impossible because when the size of your system decreases, the surface to volume ratio increases dramatically. So the friction and wear becomes a very challenging problem in small sized devices.
Maybe for the audience to summarize that a little bit, because not everybody is involved in superlubricity, and I know that we have a lot of international colleagues working in that field, like Professor Ali Ademir, but there's also people from École Centrale de Lyon, from this group with Maria-Isabelle Barros-Boucher and Jean-Michel Martin. So do you have any kind of, first question, do you have any kind of other international collaborations with these groups, or are you more or less doing your topic then from Tsinghua on and not collaborating with others, or how is that organized from the department?
Oh, okay. So first, there are actually, yes, many groups doing researches on superlubricity, but our group is more focused on a specific system called the graphite method. So the system is kind of different from other groups. And yes, of course, we have collaborations mainly with Professor Michael Urbach from Tel Aviv University and Rob Harpick from University of Pennsylvania.
Mm-hmm. And maybe for the others, just to that was originally my planned question. What does it mean, superlubricity, in terms of the friction coefficient? Where do you settle that, or where do you say this is exactly the regime where superlubricity starts? Can you somehow put that in numbers?
Okay, so that is actually a very interesting question. Well, frankly, there are many different definitions of superlubricity, and someone says that if no matter what system you have, if the friction coefficient is lower than, let's say, 1 to the 1,000, you can say that the system is superlubricity. But we have a little bit different point of view when looking at this basic problem. So, like for our system, the friction coefficient, if you define the slope of the friction versus normal force curve as the friction coefficient, we actually have zero friction coefficient because the friction is almost constant over the normal load. And basically, that's because the contact error is constant. And according to my research, if it's indeed correct? So the friction is mostly originated from the edges. So they're constant for different loads.
Will we run actually at some point into trouble when we are getting lower and lower with the coefficient of friction? And what about the measurement devices? I mean, we know that every measurement device or tribometer test rig has a certain resolution to capture, to measure friction forces. So if we run into this limit, will we then be at one moment not being able anymore to detect it because we are lacking the resolution of the tribometer? And is there still friction ongoing, or what would you say on this? It's a little bit, let's say, metaphysical question, but how do you comment on that?
So first, most of my researchers use atomic force microscope instead of tribometer, which has higher resolution in terms of measuring forces. And yes, you are very correct that this is actually a big challenge, because imagine that if you have a surface whose friction coefficient is almost zero, that means you will have a very large normal force, but a very small lateral force. So you need an equipment that has high resolution in the lateral direction, but at the same time has a very large capability of measuring normal force. So actually, yes, that's actually a big challenge. So I have an example. So we're very cared about how large the normal force can be before the superlubricity fails. And we're currently having problem to measure that critical load, because we can't measure a large normal load without losing the resolution on the lateral force.
Okay, thank you very much. I think thanks for the moment. I would also like to welcome our younger generation. I saw just before some cutie in the background. I think it was on Antje's webcam. So this is the next generation of material scientists or tribologists, whatever. But very sweet. So Stefan, so the ball is rolling to your side again. Who you want to ask next?
I don't know, Antje, is this a good time? What would you say?
We can try. He's playing here around, so at the moment he's happy.
Yeah, actually, some bird twittered to me that you're planning to come back to work very soon. Gabriele is off. Okay.
Yeah, that's true. Around about in a week.
In about a week. So I'm very excited about that, of course. And yeah, I was hoping that maybe soon we could pick up where we left off with your paper. I'm very much looking forward to doing stuff there again.
Definitely. I have now also more TM results. A little bit confusing, but
yeah, I guess we need to look into those.
Read them.
Yeah, we need to look into those.
Yeah,
so I only have stupid questions because you're the material scientist, I'm the physicist, so there's many things that I don't know. So one of the things when I was looking at your presentation and you were going into those inverse pole figures and you basically showed a time development of how the grains rotate. And you're very bent of making sure that the projection is right and that you have, you have the normal direction, the sliding direction, and the transverse direction. So, and then I can imagine how let's say the orientations of the grains can be reflected by bisectors. I can imagine that because of the symmetry of the system. But can you explain to me a little bit how it works that they creep along the boundaries when the rotations go along the bisectors? How do I imagine that? As a lowly physicist, explain it to your boy.
Oh, I try my best. So first of all, I would like to mention that it's difficult to say that it's time dependent because I measure this after the experiment. So I'm not sure about the time, so only about the place. And I know that, yeah, that the rotation is stronger or closer to the surface. And yeah, with the rotation, I usually compare this to normal tension and compression tests, because this is something I can imagine, and the stress field under tribological load is really complicated for me to imagine, as I think we also do not really have a good model. So in my group, we are usually using the Hamilton model, but this is only purely elastic, so I don't think that it's 100% true. So, and under tension and or compression, we know that a slip system has the highest Schmidt factor, which is inclined for 45-degree angle with the tension axis. So, like that. And then you have the tension. So actually, it would like to move here on the slip system. But based on the fixing, it cannot move, and this is why the slip systems rotate. And then you come to the bisector, and it's called overshooting. So you go a little bit above it, and then the other slip system moves it back to the bisector, and then it goes up and down and up and down. And so you get the textures in tension and compression. So in tensions, you get the 111 fiber, and in compression, the 110 fiber.
Okay, so actually it is a kind of a zigzagging then, apparently, and apparently this is all perfectly clear. Okay, cool.
Okay.
No, thank you very much, because that's something where I also see this in my simulations. So I actually, and sorry for implying that it's time dependent. Of course, I did remember now, of course, that you sort of have a depth gradient, yeah. But if you basically say that further down, you remember what the system was like when you started out, it is sort of like a pseudo time dependence. But in the end, it's a depth profile. I see. But with my systems, it is actually time dependent, and I see similar movements sometimes within these IPFs. So so I guess you're going to write that part of the paper, though.
Definitely, yeah. I will.
So well, thanks, Antje, very much for again putting maternity on break for already more than half an hour. So and you know, he seems to be very well behaved.
Obviously, yeah.
when nobody's looking, of course, or while he's sleeping. Yeah. Well, so thanks very much, Antje, for joining us.
So thanks also, Francesc, for joining and for a very nice presentation. So also a colleague of us, he asked in the channel itself, if I understand it correctly, the viscoelastic cylinder slides over a smooth, rigid surface, so the stress doesn't change in the cylinder. How do the high stress rates and class C state at the edge of the contact occur?
The issue here is so we are having the cylinder, and we're just sort of pulling it out of the flat rigid surface. So it's not really that it's that is sliding, but sort of the horizontal motion comes because as the cylinder is pulled out, then the contact area is shrinking, and so if you put if you track the contact edge, which is where adhesion happens and where you have the highest stresses. So this point is actually moving, but not because the cylinder is sliding, but because the contact area is retracting.
Okay.
So in that sense, it's also moving with respect to the cylinder body, and hence it's producing these high stress rates, and then it can lead to for the material at very near the contact edge, which again is moving to be in the glassy state.
Okay, thanks. Now, I saw on one of your slides that you selected Dugdale-Mogis model to start things. I was wondering, I'm not an expert in these adhesive contact models, but I remember from my studies, I mean, there is JKR, there's DMT, and I know in this Dugdale formulation that you actually have a kind of, how's that called? You have a cohesive zone where the the work of adhesion is actually the product of this sigma 0, which is the maximum force you get multiplied with the maximum separation H0. What would happen if you change actually from a ducktail approach to JKR or DMT in that respect?
Yeah, so it's actually a bit two different things. So when you're looking at JKR or DMT, then you're talking about two different limiting behaviors. Whereas a cohesive model is a sort of a stress separation law that can be used to model that in between. If we think at the JKR, it's the limit where adhesion is very short length. So that it's really only when the two bodies are really touching, there can be an adhesive interaction. Whereas the DMT limit is the opposite. So you assume that the body is almost rigid and there is only attraction in the gap, if you want. So what the ducktail model is allowing you to do is to have a bit sort of an in-between situation where you have the bodies deformable. When there is contact, there can be a certain adhesive interaction. Outside of the contact, if the bodies are close enough, then you also can have some level of attraction. But then what you can do is with ducktail is you can play with the length scale where this attraction occurs. So if you make this length scale very small, you eventually reach the JKR limit. Whereas if you make this length scale very high, you would reach the DMT limit. But then, of course, what you can also wonder is whether this ducktail adhesion law is the only one, or you could have taken more sophisticated traction separation laws. And actually, it's usually not a very big deal because you're always forming at the edge of the contact this very narrow spike. So a bit regardless what potential you use, you're still going to have this very narrow spike. So the actual shape is a bit inconsequential.
What would you say is one of the major limitations or drawbacks actually of the ducktail approach? Is there something you can word up in? We say, okay, I mean, we know about the limits that you explained right now, the lower boundary and the upper boundary by JKR and DMT, but for the situation in between, is there anything which comes into your mind where you say, okay, this is one of the major disadvantages or drawbacks, limitations of the ducktail approach? Or is that generally hard to say and is case dependent? Or
no, I mean it's more that they apply at different places. So I mean the sort of JKR limit, which is the one I'm getting close to, that's usually used more in analytical solutions. Whereas in numerical approaches, as in the case that I am using, you can simply not reach that because it's a limit of zero interaction length, which of course you cannot reach numerically. So in that sense, you're forced to use a finite interaction. And that's one of the main difficulties when working with analytics and viscoelasticity, is that when you work with these limits, like the JKR limit, you're having this infinite peak stress at the edge of the contact. And that means that if you have an infinite peak that's moving at a finite velocity, but I mean, even if it's a very slow velocity, but still finite, the stress rates that you will have are going to be also infinite. So you're going to lose the velocity dependence, which is something that's observed experimentally. So in that sense, it's not so much a matter of advantages or disadvantages or one or the other. It's more that you really have to use either ducktail or another type of cohesive zone law, because otherwise you cannot reproduce any sensible results. So it's a bit of a must if you want.
Okay. Okay. Yeah, thank you very much. I have the impression that for many people, this is somehow scary stuff. I could also see that not many people send questions related to the talk, although I find it very interesting, and I have deep respect for people who are very much in the details of these models. So thanks again for participating, and thanks
Well,
also.
it's always a bit that when you're very deep in the topic, it's not so scary. So for me, also some of the topics were, I don't know, with this twinning or stuff like that, were also looking quite scary. That I'm not involved in that. So.
It looks scary because it is. Well, thank you, Francesc. I mean, it's pretty cool stuff.